to lecture 5. Today we're talking about programming paradigms. Brian on Monday mentioned the functional programming paradigm, and I'm here to tell you that just one of the examples of the other programming paradigms there are. So I always try to have a news of the day, and on the theme of games and video games and 3D graphics, I saw this really cool post on Slashdot. By the way, I recommend you read Slashdot if you're into kind of tech news, which is really fun to keep up with that stuff. Intel, I mentioned that global illumination is one of the rendering models that allows you to have reflections and shadows that are very accurate and has imagery that's kind of closer to what the real world is. Well, it's hard to do in real time. I mentioned that there's some people who are doing some cool hacks to get to there. But ray tracing is one of the things that's very hard to do in real time. It's where you trace rays all the way through, bouncing through, and get really beautiful, accurate shadows. As you can kind of see here, if I maybe zoom in on that picture, there's some beautiful shadows of the tree, middle one, I think that, yeah. The tree on top of the car. So it's a gorgeous picture if you look at the full image of it. And Intel has decided that wouldn't it be cool if you played a game, so rather than have all the work be done by your graphics card that showed in the Take Apart the Computer discussion section, but wouldn't it be cool if the work was actually done on the cloud? So you're in a browser and you're making your video game and you're going from here to there, and all of a sudden you're looking at this gorgeous shadows. You realize this is being ray traced. And who is doing the job? Who's doing the work of generating all those shadows and generating the picture? A massive set of computers. Isn't that cool? So it's rather than one computer with one graphics card, you are using the cloud, and the cloud's doing the work. I think that's really, really cool. Okay, great. As people come in late, by the way, we try to squeeze in, like we mentioned the first day, because I think when people come in late, there's a lot of hustling and bustling. So as you come in, kind of push yourself to the edge to leave the spaces in the aisle. Thanks, folks. So today, Programming Paradigm Lecture, we're talking about the paradigms, what they are, at least kind of to put them on the stage. The 4 primary paradigms we typically talk about, and there are actually other classifications. But these are the big 4 that we've always talked about. Functional, as Brian mentioned on Monday, an imperative paradigm, an OOP, or an object-oriented paradigm, and a declarative paradigm. We're going to talk about something called Turing completeness, and then close with a summary. So, what are the paradigms? Well, a programming paradigm is, and I don't want to read you the quote, but it says, it's essentially how you look at your program. It's the way you interact with variables and state and assignment and keep track of control flow. Keep track of those things, environment variables, and it's how you interact with them. So it's the control flow that goes through the how you tell it. So it's kind of like how you store the data and how you tell it to do stuff with the data, essentially. Kind of neat. The other way to say it is the way you classify the style of programming. So, clickers. Let's get the clickers out, and I will launch it now. And the question is, of the 4 paradigms, how many can BYOB be? You know that Scratch is the early version of the programming environment you're using, and we're moving to BYOB where you can build your own functions. So, how many can BYOB be? Hopefully we're going to get way past 60, because I think we're at about 70-something, so hopefully we can get up to that range in terms of all the students in the class. Anyone raise your hand if you don't have a clicker? Some people did join late. Oh, okay. If you didn't get a clicker, talk to UTA in lab. They'll get your clickers. You still have some extra, I guess, right?
Mm-hmm.
All right. So this is more of a sample question, not so much of a discuss question. There will be a discuss question later on in the lecture. 57, all right. We'll go for a minute and freeze it. All right. So what'd you say? Look at that, it's pretty evenly mixed. Interesting. Good stuff. Well, I wiggle here. 4 is the right answer. BYOB can be all four of the paradigms we're going to talk about today. So that's really cool. That means if you wanted to say, oh, that sounds fun, I want to play with that in BYOB, you can. Love it. Do you want to go with that? Okay, very good. Okay. So, most languages, a la BYOB, are hybrids. And a hybrid language is one that isn't a pure one of the four I've mentioned. It kind of can be one of them if it wants to be. If you want to live purely in the functional domain, you can. Or it can also be something else if you want it to be, which is really cool. So that's nice. People have realized that you want to pick the right tool for the right job, and they might be used within the realm of BYOB. There might be times when thank you very much for being loud down the hall. When in a particular programming environment, you want to be able to program in a way that's different than you have before. You want to program in an OOP way for this particular project, but not have to learn a new language for that. And that's great that you can have these hybrids that do that. And the reason I say it's like giving somebody a juice drink and asking them to tell the flavor, right? It's hard for you to get a feel for what these paradigms are if you're living in this hybrid world, right? If you're BYOB and sometimes you're functional, and sometimes you're imperative, and sometimes you're OOP, then you don't really get a feel for what the purity of one of those styles are. So it's kind of like trying to figure out what the flavor is in a fruit drink that has all those mixed together. So, this is a review of what Brian said on Monday. Functional programming is a delightful way to think about the world in that you go back to the world of functions. And I want to try to, Brian made a point to emphasize that this isn't just about numbers. You can calculate functions of anything. But here's an example of trying to do this on, am I on a battery? I think I don't have a battery in this guy. So I'll use the cursor. Here's a function f of x is 2 plus 3 times the square root of x. And so I can think of this as a black box, right? As a black box. X comes in, and that function of x comes out. I think of it as like plugging in different pipes together. It's almost like you're the plumber. And you have these pipes, and every function has exactly one output. Okay? Multiple inputs, maybe no inputs, exactly one output. You're basically just plugging these pipes together, and water just drains, and data just drains the right way until you have one output at the end. It's beautiful. Functions can be the input. That's a really powerful idea we're going to see later on. I think Brian alluded to a little bit on Monday. The features are, there's no state, so there's no kind of memory in the system. The same values input should get the same values as input, should give you the same output values. There's no changing of variable values, not kind of, here's the state, I'm changing this over here, and let's remember that I have some state, and that state allows me to mutate those variables. And there's no side effects, which means you're not printing to the screen, you're not making a robot move, you are just bringing it, have a value, a beautiful value at the end, nothing else is happening. You're not printing something to the printer, just values coming out, okay? And the examples are Scheme, which is a really beautiful language, and Scratch, BYOB, if you live in this functional world. So here's the way I think of it. To build this function up, well, I have a plus guy that's in there, and I have a square root guy that's in there, and they're all composed together. The values of those two guys goes into another pipe, another function called the multiply function, and now 2 and 3 get set to the inputs of the plus guy, and x gets fed to the input of the square root. So essentially you can think of this, and the beautiful thing about living purely in the functional world is imagine that picture and then zooming back and say, okay, f becomes just one of these cyan blocks in a larger computation. And that larger computation just becomes a small cyan block in an even larger computation. Isn't that cool? So you can just keep zooming back. It's as if you zoomed in here, and these are the primitive operations. And as I zoom really, really, really far back, you'll realize that f is just one piece of this wonderful large cog of things. And that's functional programming, right? All that's a review. Hopefully any questions about that? Hopefully no concerns about that. You've seen that before. This is the first time I'm telling you a new paradigm you've never seen before. But you probably have because you've been playing with Scratch. The imperative paradigm, also known as a sequential paradigm, sometimes even known as the procedural paradigm, is a series of steps. It's like a recipe. The goal is to do some job, and you do it by this step, and then this step, and then this step. And each of those steps is probably setting some local variable, you're changing state, you may be mutating these variables. For example, that same f of x, here's how you do it in a typically imperative style. Well, let's have an answer so far. The answer is what I'm going to return at the end of the day. Let's set it to x. Well, this assignment was never allowed in that world. You never had an assignment. You just return things and plug them together. There's no assignment in functional programming. This is what we have in imperative style. Let's let the answer be x. And then let's set the answer set to square root of answer. So now I'm kind of doing the square root of x part of the computation. And then let's multiply answer by 6. Okay, 5. And now that is f of x. Answer is your f of x, and I return answer. So these 3 steps is the imperative style of doing things. Okay? One of the things you saw in the functional world is that can be parallelized really, really well. Well, imagine this, where I parallelize this and some other guys are doing something, but answer is, say, a shared global variable, let's just say. And somebody else is using answer maybe as a temporary variable for their computation. And they're coming in and running at the same time I am, and all of a sudden, my values of answer aren't the same because both of us are kind of changing answer. That's why that's hard to parallelize. But this world, there's nothing in here that has some state. I'm just plugging the things together, and there's no worries about having somebody else in there because there's no equal sign. So there's no worries about somebody stepping on somebody else's foot. Love it, right? Okay. An example of this with Pascal and C. The third paradigm is called OOP. And OOP became all the rage. It became all the rage. Back in the mid-'80s, when C was very popular, it was an imperative world. It was a Pascal and C imperative world. People were happy. Functional people still were around at the time because Lisp predates all of those things. But C and Pascal were very popular in the mid-'80s. That's what everyone did. And all of a sudden, and by the way, people had been doing OOP kind of in the research labs and publishing papers about them, but it really hadn't hit the mainstream. The average Joe programmer wasn't programming OOP back in the mid-'80s. And at some point, enough people said, you know, that's really cool. We should try to do this. But we have a whole world of people who are programming in C. What can we do to add this OOP to it? Well, they said, in C, the way you increment a variable, if a variable, let's say call it C even, variable C has a value of 5, you want to make the value 6, you'd say C equals C plus 1. Right? So now that value was 5, it's now 6. Another way to do that in shorthand is C++. It means C equals C plus 1. Just shorthand for C equals C plus 1, C++. Well, guess what? They decided to call the language that, to imply that it was C plus 1. You get it? The language C plus C. This is funny for most of us computer scientists. They all laugh, and that was very clever. So C++ is the language in which you try to add object-oriented programming to this imperative language. What is object-oriented programming, Dan? How much of the history? Tell me what it is. Well, the world of objects. Should we close it? I know it's so hot, but it's loud. What do you think? Close? I can't hear, right? Close? Okay. So painful. Okay. They're moving things in. There's a whole U-Haul truck of lots of loud, noisy bells and things. All right. I apologize, by the way, how hot it's going to get. Okay. So here's the idea. You've got a world. The world is the real world. Like people, and you have chairs and dogs, and the way that world interacts is people send messages to each other. Hey, Luke, can you wave? And Luke waves. And then Luke says, Dan, can you wave back? And I say, hey, Luke. And we're both kind of communicating by sending messages back and forth. And Luke also has some state, some internal values about himself. I know Luke has internal to the Luke, say, object. He knows how much money he has, and I know how much money I have, and those different numbers maybe. And he has a name, and I have a name, and those are different. And all of us have names and money in their pocket, or none, and other features about yourself. So all of that means that if you wanted to simulate a world where all of us are walking around and maybe I pick up some object, and this object is now part of me because it goes in my pocket. And now you can ask the object, whose pocket are you in? Let's say Dan's. It's kind of cool. So that world is one that kind of simulates a real world scenario where you have objects, kind of things like a person. They have state about themselves, like their name, like the amount of money they have. They have behaviors they can do, they can respond to messages, and they have a way to kind of communicate and pass messages to other objects. Isn't that cool? So the way this works in kind of most languages, you have classes. Classes are the way you make objects, like a factory. They're just wongada, and then objects are pumping out. Another word for objects is instances. It's the actual object is around. It's called an instance. So a class might be a dog. I'm a dog factory, wongada, but that particular dog is an instance, Fluffy. Fluffy would be an instance of the object dog. Okay? And you could ask that dog, sit. You're very common, right? Sit, stand, bark. Exactly. It can respond, or if it's a cat, not respond to the messages you ask it. There's an idea of inheritance, and inheritance is weird, but it means that objects have a natural way of kind of falling into a tree, kind of hierarchical tree, in which you can think of the army. You might have, well, my example here is, you have a pianist, and the pianist is an object, and you can have a factory that pumps out pianists, right? Or you could say a pianist is actually just a special case of a musician. So if you already had a musician with certain properties, like what school they studied at, what instrument they play, then a pianist is really just a special case of that, right? And then you can think of this, a musician is a special case of a performer. A performer might have an entourage, it might have an income that's very great, and the island they particularly bought because they're a performer and they did that. A performer might be a special case of a person, and the person has some properties. So all these things can be shared. So rather than having to implement for a particular pianist, hey, tell me your name, and the pianist knows how to say their name, the pianist doesn't have to do that because the pianist is a special case of a musician. Musicians can also say their name. So can performers. So can people. So let the people class deal with how to say your name. And if you're a person, you know how to say your name, right? Hey, say your name. Luke. Okay. So that's the person's job, not necessarily the pianist's job. So if you're doing pianist class, you don't have to worry about that. Somebody else can handle the job for you. So rather than repeating that code in every single possible class, you can let somebody else handle that for you. That kind of makes a little sense. So it's a way to share code, not to have redundant code, because of this hierarchy you can take care of it. It's kind of cool. So that's the big idea. Here's a little picture of it. Names, attributes, behaviors. I mentioned that kind of attributes are the money and the name, and behavior is the things you can do. So I want to show you a little bit of this course is about historical information. It's really important that we know history. Okay? So it's also cool, it's also really important that you know the most impressive piece of software ever written for its time. Okay? I'll say it again, the most impressive piece of software ever written for its time. And that's this piece of software. Written by Ivan Sutherland. Ivan Sutherland is the father of computer graphics. That connects up with the lecture we had a week or so ago. Okay? The father of computer graphics, Ivan Sutherland, who decided in his retirement, where should he spend his time working with the smartest people, working on the cutting edge parts of architecture? Oh, I don't know, ECS department, UC Berkeley. Thank you very much. So he would be around the halls. It'd be so cool to see this father. I would sit next to him at lunch. I would say, he's the father of computer graphics. And it's so cool. The entire field was this one person. Thanks to this one project, and some other work he did. He was really fundamental in founding graphics, but this thing got it off the ground. It's very exciting. So let me show this to you, okay? And I'm going to come back to these 3 bullet points, which is so cool. But here's the reason I'm showing it to you. The first object-oriented system ever. Okay? So let me show this movie. By the way, this is Alan Kay, a Turing Award winner. Turing Award is the Nobel Prize in Computer Science. And Alan Kay is introducing Sketchpad in one of his lectures he did, I believe, in 1987. So a long time ago, but still, and he's saying, man, this is amazing, best thing ever done in 87. I'm showing this video saying it's still that good. Okay, Alan Kay, everybody.
Something else was happening at Lincoln Labs in 1962, and that was the invention of computer graphics. Ivan Sutherland's Sketchpad, probably the most significant single thesis ever done. A remarkable program in many ways, even today, as we'll see by looking at this tape. This tape is from the very first movie of Sketchpad, taken in the summer of 1962. So this is 25 years old. Rubber bands you're familiar with, but look at what he's doing. He's pointing at the edges and saying, I want them to be all mutually perpendicular, and Sketchpad just figured out how to do that. Sketchpad is the first system to ever have a window. He's actually drawing on a virtual sheet of paper about 1/3 of a mile on a side. And again, to get something he wants, he simply sketches it in roughly and then gives rules like be parallel and perpendicular, and Sketchpad figures out and solves the problems. Here the rule is collinearity, so that the dashes lie directly over the guidelines below. The Sketchpad was able to solve very complicated problems in real time involving both linear and nonlinear systems of constraints. So it was the first non-procedural programming system and considerably more powerful than the spreadsheets of today. So he's made a hole in the flange, continuously zooms back. Now he wants to make a rivet, and again we see why it's called Sketchpad. He just draws a rough shape, uses the center of the crossbar there as the center of the arc, and then points to the edges and says, I want these to be mutually perpendicular again. Solving that forces the crossbar to change, which forces the arc to change, which gives you a perfectly symmetrical rivet. And he shows that no matter how you distort it, when he turns the problem solver on, it will come up with a symmetrical solution. And he could have made it more complicated in the environment. Now, another important idea seen here for practically the first time is that of master drawings and instances. He was working on a master drawing, and what he has here now is an instance of that. The instance can be rotated and scaled and positioned. So he's going to insert the rivet in the hole. By the way, the Sketchpad was the first system in which it was definitely discovered that the light pen is a very bad input device. So the blood runs out of your hand in about 20 seconds and leaves it numb. And in spite of that, it's been reinvented at least 90 times in the last 25 years. Here's another instance back then. The TX2 is putting up every dot by brute force. He didn't like the cross pieces, so he goes to the master drawing, makes them transparent. Lo and behold, we see dynamically that the rivets, the instance rivets, have felt that change. So Sketchpad is also the first object-oriented software system. I once asked Ivan Sutherland, how could you possibly have done the first interactive graphics program, the first non-procedural programming language, the first object-oriented software system all in 1 year? He said, well, I didn't know it was hard. There's nothing like this before. And here he's showing that every instance that you make of something, every master can create instances. So he's making a bunch of copies of the hole in the flange. Now, I'd like to tell you where you could go to buy a system as good as Sketchpad, but I don't know where, because there isn't anything like it even on the market today, 25 years later. It was a one-of-a-kind thing. It ran on a machine much larger than the studio that I'm recording the talk on. In fact, it was the last computer large enough to have its own roof in the United States.
Pretty cool. So that was Sketchpad, and in summary, first object-oriented system, first graphical user interface, kind of starting the field of computer graphics, and first non-procedural language. So pretty impressive piece of work for a thesis. So you're going to say, well, Dan, that's all well and good. You did tell me, you alluded to the fact that BYOB can do oop. I think I turned the wrong light on. Is that right?
Mm-hmm.
This is
Just the far right. Leave the far right one on.
okay.
Brilliant, thanks.
That's right.
Good.
Thank you.
Well, you are probably not going to understand this. I think Brian showed a little bit of this before, but let me just tell you roughly what's happening. With this code up here, which you will understand by the end of class. So it's kind of fun that this might look like gobbledygook, but you'll understand by the end of class. Let me walk you through it. I first make a local variable called count. I set it to 0. And then I don't return a number. I don't return a word. I return a script. And that script bundles up. It's weird to return a script, but it's returning the script of change the count by 1 and return the count. It's a script being returned, not like a function being returned. Okay? Now, I then make 2 counters. Counter 1 is new counter. Counter 2 is new counter. When I say new counter, it's actually calling new counter and returning this script once here, calling it again, returning another guy here. So counter 1 and counter 2 are 2 different return values of the same guy, right? But the question is, are they different or the same? So let's look at it. I'm then going to say, say, call counter 1 for 2 seconds. And it says 1. Why does it say 1? Well, calls counter 1. Remember, this is a script. This is like a program of return. So it's going to say the return value of this thing. Let's call it. Ready? Change count by 1. It was 0 initially. Now it's 1. And return count. So love it. Let's now do it again. Let's call counter 1 again and see what happens. What does that return? Well, it returns 2. And our character, Berkeley, Brian? What's his name?
That?
Yeah.
Alonzo.
Alonzo. I'm sorry, that's Alonzo, right? Okay. Alonzo, remember why it might be called Alonzo? Alonzo now says 2. And do it again. Say, call counter 1, Alonzo says 3. But now, here's the cool part. Think, call counter 2 for 2 seconds. So counter 2, in theory, was another call, a separate thing. Let's see if it is a separate thing or not. Well, does it say 4 or does it say 1? Sorry, it says nothing. Does it think 4 or does it think 1? It thinks 1, because it's a different script with a different local count variable. Your mind is going, what is this? Because you're not ready for this until week 12. But I'm giving you a sense that this is what you're going to learn in week 12 and how it works. Kind of cool. It's a little bit of a foreshadowing. So don't worry, you're like, zoom. Hands ready? Zoom. Can we all make the motion? Zoom. Okay. If it's okay, no worries. But we're just telling you in case you're ready for it. Then I think counter 2 again, it's 2. And I go back and I now think counter 1 and it's 4. So they both had, what did I say? Objects have their own local information, local state. I just made the simplest object. It all has is a number. And guess what? Those 2 objects were different, right? One is now 4 and one is now 2 as a result of that interaction. Object-oriented programming in BYOB. Thanks to Brian and Jens. Brian was the co-author of this, and Jens is the co-author of BYOB with a lot of input from a lot of folks in the team, but those are the main architects of the program. It's pretty cool. BYOB also allows you to send a message to a sprite. Your current value of BYOB allows you, I believe Scratch allows you to query. Does that exist before?
The of block is a
the of block is a Scratch thing where you can
Not
say,
with methods.
let me query what the X position of this girl sprite is, and it might return a value, and you could use that in if you're another sprite. But the power of BYOB is I can define a custom block. You can't even define a block in Scratch. You can define your own custom block in BYOB. I had a girl character, girl sprite, and I had a little dance script. She does a little boogie boogie. And I can now reference not just the variable, the X position, Y position, its loudness, whatever they add locally to that. Maybe loudness isn't one of the local sprite variables. But I can reference one of the local scripts called dance. And I can now run. So this Alonzo can run, basically send a message, right? That's what this is about. Send a message. Hey, girl sprite, can you dance? Girl sprite starts dancing. That is so cool. So here it is, OOP in BYOB. Question about it.
So is script more like, with what we were talking about earlier, is script more like a class and variables or like the instances?
A script is a function. You want to think of a script as a function, and by having a function that returns a function, and by packaging this local variable up, I can get to the fact that this guy, this new counter, is the way, this right here, what's left in the top part, that's your factory. That's making counters. This call to counter makes a copy of this and sets it to counter 1, and that's a local copy of an instance. So new counter is a class or factory, but the word script is really a function. And by packaging it a certain way, you can make it a factory.
It's not a function.
It's not a function because it has state, it's a procedure. Okay? Good. So, 4th paradigm. How are we doing for time? Perfect. Declarative. So it's the last one we're going to talk about today, declarative programming. Now, declarative is really the most different of any of the other ones. And declarative is the one that's had the hardest time gaining traction in the programming community. You'll find people out in the real world programming in a functional way. You'll find folks programming in an imperative way, folks programming in an OOP way, but very few programming in a declarative way, just in terms of the raw number of people out there doing stuff. But what is it? It's a really powerful idea in which I don't tell almost every other language, you're caught up in the minutia of telling the program how to do something, how to sort a list, how to make the number bigger, how to compare to something, how to do this, how to do that. In the declarative world, you don't tell it how to do it at all. You just tell it what you want. And almost by magic, the right thing happens. Okay? Now, there's not real magic in there. There is a program below the line, below the abstraction line that's actually doing the work of doing it. But you as the programmer don't have to tell it how to do it. It just gets done. What's often used is a series of assertion and queries. That's the most typical use of declarative programming, in which I assert some facts, like people like to be around other people, and they like to have food 3 times a day, and they like their parents, except not always, and they like movies, and they like sports, and they like big screen TVs. And I could just add these set of facts. And then I could say, does a person like to be alone on Sunday? And it might go to my list of things that I said. It says, the answer is no. Why? Well, because you said that they like to go to church, and church is a social thing, and so that's probably they're not going to be alone on Sundays. Or they like to watch football, and football is a social thing because you bring your friends over. And because of these facts, it might be able to answer facts almost in an AI way, in an artificially intelligent way. So it feels like magic. I didn't tell it how to calculate, so I just told it some facts, and I asked it a question. It was able to use that. Let's actually go to a real example. So the subcategory is logic and constraint-based. We saw some constraint-based programming in Sketchpad, actually, where I said I want these 3 guys to be mutually perpendicular, and it all worked its way out. That was a set of constraint-based programs. So let's actually look at this. Have you ever seen this kind of a puzzle before? Raise your hand if you've ever seen a kind of puzzle like this before. In which I have, let's read, 5 schoolgirls sat for an examination. Their parents showed an undue degree of interest in the result. They therefore agreed that, in writing home about the exam, each girl should make 1 true statement and 1 untrue one. And the goal is to figure out how they did in the exam. 5 girls, 5 rankings. 1, 2, 3, 4, 5. No ties. Okay? And so you have these girls saying, Betty says Kitty was 2nd, I was 3rd. Ethel says I was on top, John was 2nd, etc. And it is the case that of these 5, there's a unique answer, and that's all you need to know in order to determine that unique answer of the placement of those, how they kind of paste on the exam. Okay? Who's seen this kind of thing before? Who likes these kind of things and these are fun to work on? Okay, cool. Well, I'm going to show you a system that'll solve them for you. How about that? Also written by Brian Harvey and a team of talented people at Berkeley. It's called UCB Logo. And all I'm going to tell it is the following fact. This is what I'm going to tell it. This is the way I'm going to encode that problem into, this is called logo, this language logo. Okay? Let's look. So you can see from up here, I think it says here, okay? Betty says, Kitty was 2nd, I was only 3rd. Okay? So here's what this is doing. Don't need to worry about this. You're never going to be asked to program in logo, but this is just the way that we do it and express this in logo. To keep track of the following track, and basically set this up and try to solve, I have 5 people, Betty, Ethel, Joan, Kitty, Mary, just like you heard of. I have 5 different places, and what track's going to say is that these 5 are going to somehow map to these 5. So there's going to be some kind of mapping where one of these has to be one of these, and uniquely, right? One of these guys has to be one of these guys uniquely. Here are facts I'm going to state about the problem. Not equal, forget the P, not equal, Kitty is 2 and Betty is 3. Let's think about that. Betty said, see, Betty's first person to speak. And we know that Betty is not saying 2 true statements or 2 false statements. She's saying 1 false and 1 true. So, is Kitty 2 returns a true or false thing? Kitty's either 2 or not 2. Betty is 3 is either true or false. Betty's either 3rd or not 3rd. And what I'm saying with this statement is, these are not equal. That kind of makes sense? Which covers the case of this being true, this is false, or this is false, this is true. It's kind of a clever way to do it. Rather than say, well, this is true, or this is false, or this is false, this is true. By saying they're not equal, it kind of covers that case. It's kind of nice. Similarly for every line. Ethel's 1, Joan is 2, and Ethel says, I was on top, Ethel's 1, and Joan was second, Joan is 2. Okay, etc. All right? Tell me where I explicitly tell it to go through all the cases and match them up. No, nowhere. The system is declarative. I say some facts and I ask a question about it. So what track is going to do is, after this set of facts, return anything that it can in terms of the matchings of it. So, let's try it. Copy this, go to logo, paste, and I wait. I wait. And I might have to return. Maybe I have to return here. Oh! Whoa. You kidding me? Betty 3, Ethel 5, Joan 2, Kitty 1, Mary 4. And now we can see if that's actually true. Here's the statement on top. Here are the results. Let's see if it worked out. It should be exactly one true statement for each one of these guys, right? So let's see how this works out. Betty, so the first one says Kitty 2, Betty 3. Betty 3, Kitty 1. Nope, only one of those was true. Ethel 1, Joan 2. Ethel 1, nope, but Joan is 2. Got that case. Joan 3, Ethel 5. Ethel 5, correct. Joan 2, that's incorrect, so that's perfect. Kitty 2, Mary 4. Nope, Kitty 2, but Mary is 4. And the next line is Betty 1, Betty 4. And Betty is not 1, but Mary is 4 again. Isn't that cool? Take a bow, UCB logo. So that's awesome. I never told it how to do it, it just figured it out. And that's the declarative world. Isn't that kind of cool? Very powerful. You can see why that would be useful. If you ever set a constraints, I want to see if I can build a bridge. You can imagine a system that says, I need to be able to span the Golden Gate Bridge, build a new Bay Bridge, and I have this cost, and this is how much it costs for materials and concrete and steel. Can it be built for this amount of money? And it'll return, nope. Because it knows the cost of that just won't work out. You can do this for a lot of real world things other than just solving logic puzzles. I could say, patient shows abdominal distress, a blown pupil, vomiting. They love CS10. What's wrong with them? No, I'm joking. They hate CS10. I should have spun it better. Isn't that cool? And the system would say, they probably had a massive blow to the head. Isn't that cool? That's pretty amazing. That's called an expert system and very related to this kind of world. There's a question there. Yes?
Yeah, is Logo built off of Prolog, or is it just an example?
No. Prolog is its own thing. It's its own kind of declarative world. You can download a program, Prolog interpreter. Logo is another language for kids, really, to draw turtles around, just like BYOB was. And what they did was they put a layer of declarativeness on top of it. So, just as BYOB in theory could do. Of the 4 paradigms, this is it. This is the real question. This is where we're going to have some discussion and some fisticuffs, and you got to have a consensus. Ready? Of the 4 paradigms, which is the most powerful? I will now start the voting now. This is deep.
People seem pretty confident. Lots of
Wow.
numbers coming
Yeah, I
in.
love it. No, it's good stuff. You should see the numbers here. It's really fun.
What did they?
I can see the rough ratios of things here in the front. It's kind of fun to see. All right. 56. We'll go to 60 and we'll stop it. And 60. Okay. Talk amongst yourselves. Talk to your neighbor. Make sure you know their name. Go. Your job is to convince them about your belief, and they convince you about theirs.
Got it.
Got it.
You're done.
What'd you guys say?
Yeah, what do you guys think?
Okay. I hear the discussion's kind of coming to a hum. So let's now vote again. You have to vote the same as your partner. Okay? Consensus. Consensus building people. Go. Normally I usually do this.
Come on, Lily.
Oh, I like it. This is going to be really fun to watch the deltas.
Like we still do. Yeah. It's still an imperative style.
Love it, love it, love it.
Object oriented.
All right, so let's stop and reflect. This is what you said on question 3, and look at the shift. Look at that shift. Right answer, E. Ah, don't you love the clicker? There's something called a real-time on the fly. Here we go. Here we go. Clickers. Question. Don't you just love them? Okay. Here you go. Here we go. This will be the fastest one. A. Yes. Question mark. B. Yes. Maybe. C. Neutral. D, no, and E, no, exclamation point. Okay, here we go. Ready? How fast? Ready? Go. Don't you just, free, by the way, free. Keep in mind they're free. Why do I emphasize, again, that they're free?
I really like that they're free.
Okay, let me just let you know. By the way, if you didn't know, they were free.
Some people are saying
Right
no.
when you said that, it like
Yeah, it
skyrocketed.
spiked. It better spike. It better spike, people. I'm charging next time. All right, here we go. Good stuff. All right. So here's what's so cool. This is the most, probably this is the stuff that's gonna blow your mind. All right, let me introduce you to this weird, like 18th century computer. It is called a Turing Machine, and all it has the ability to do, it has these 2 reel-to-reel tapes, okay, with big bits. You know there's bits in the computer, 1s or 0s, but the bits are so big you can see them. 1, 0, what, huge, okay? 2 reel-to-reel tapes. All the computer can do is run a program, and all it can do in that program is move the tape to the left, move the tape to the right, read a value, and maybe affect what you do in your own program, or write a value to the tape. It's called a Turing Machine, okay? Named in honor of Alan Turing, famous English computer scientist and theoretician. Okay. This Turing Machine, with just that simple mechanism I've described, I have to almost pause for this, it's so powerful, can simulate any computer program ever written in the past, ever written in the future. I'll say it again. That simple idea of this tape moving left and right, reading a value and maybe thinking about that value and doing something based on that, meaning changing one of the 4 things it does based on that value, and then writing a value, can do any computation we've ever asked a computer to do or will ever ask a computer to do. Okay. Now, we call this a universal Turing machine that takes as input a Turing machine, right, with its own program inside, right, like that thing, and the input that it was going to run on in the first place, like the tape or the input that was going to run in the first place, and will run that input machine on that input. Okay? So it's a method, it's called a universal Turing machine, takes as input 2 things. One, a Turing machine in the first place, the actual machine, and an input. And I'll just work it through. I can chug it, run it through and simulate it, okay? A language is considered Turing complete if it can simulate a universal Turing machine. So if you have a language that has the ability to kind of pretend like you have this long tapey thing, and you can read and write a bit, and move the tape left and right, if you can do that, which is very minimal, that's a pretty low bar, right? It's not like, can you draw a window with a sphere? No. Can you simulate this universal Turing machine? If you can do that, then you are Turing complete. And if you are Turing complete, then you have reached the ultimate of powerfulness for a language. So, if you go to a programming language conference and someone says, they stand up on a soapbox, they say, I am about to announce the release of a new language, and it's going to be more powerful than any language ever. You laugh, because you all know that there's no way any new language in the future could ever be more powerful than the existing languages because they're all Turing complete, and all the language you're playing with, Scratch, Prolog, all these things I mentioned are Turing complete. Okay? BYOB, C, C++, Java, they're all Turing complete. So no one could ever stand up on a stage and say, I have a language that's more powerful because you know that Turing completeness means it's as powerful as we'll ever need. Isn't that cool? So there's no discussion of, oh, well, this is more powerful than that. You can say this is easier to program in, more fun to program in. I have a smile on my face when I program in it. You can say those things, but you cannot say it's more powerful in that you can express things that you could not express somewhere else. Does that make sense? That's pretty cool, and really big idea in computer science. So a good time to kind of make sure you know about that. So, 4 paradigms: functional, imperative, object-oriented, declarative. The way to remember them: functional, plumber, functions together. Imperative, first do this, then do that, then do this, then do that, then do this, then do that. Object-oriented, send messages between things to simulate kind of the way the world works in some sense, of objects and pending messages and real-world phenomena. And declarative is ask it a question after you've given a set of facts. So, in summary, each paradigm has its unique benefits. And these benefits might be in ease of use, or in how few lines of code it takes to express the problem in that language. That's great. It might be really hard to program in a universal Turing machine. Right? It might be hard to write a Turing machine that can do that. But you could. It's just annoying and really hard and painful. So we build layers upon layers of abstraction to make it an easier process. Here's a Tower of Babel of all the programming languages that have ever been created. If you come up here, it's amazing how many programming languages have existed and are continuing to be born every day. Yet, no, because of the wonderful idea of Turing completeness, none is any more powerful than the other. Just ease of use and different small features about that. Okay? In summary, modern languages usually take the best from all, and Scratch can be all of these guys. That's pretty cool. On Monday, 12 o'clock. On Monday, in this room, please get here early. Those of you who come here late at stragglers, please leave your class early because you have a quiz here. It's called a quest. It's going to be on all the material up to Monday. So all the material through this week. Everything in this class is fair game, except discussions, because we let the discussion leaders lead the discussion in the way they want to, and so one might take it this way, one might take it that way. It's not fair to test them on both of those things. So, except for discussion, everything is consistent in this class, and it's all fair game. You may bring one single sheet of 8.5 by 11 paper. If you are someone who has a conflict at this time, meaning you're somebody who normally doesn't come in here but watches the lecture via webcast, but you're still enrolled, I hope you're hearing this message. We'll send an announcement to make sure you hear this. We'll make some arrangements. Please email me or email one of the TAs to make arrangements for you. Questions back quick before people should go. Includes the labs. Reading assignments, lab, lectures, homeworks.
Homeworks, right.
Okay? Everything you've done so far. It should be very doable if you've been going through all the labs and all the discussions and doing all the readings. It should be like this, piece of cake. Piece of cake. Okay? We'll see you guys on Monday. Have a great weekend. There's a review session on Sunday. We'll send out information about that. For those of you who want some review and need some kind of like, oh my gosh, I need some help with that. Review session on Sunday. We'll send details about that.
Citrus is closed.